Hi guys, today I'm going to show you how to construct a soil structure interaction model in ABAQUS. The soil domain is 40 by 40 by 30 meter, and the structure is a very simple 3-story concrete frame, and the foundation is very simple spread footing. And each footing, the size of each footing is 2 meter by 2 meter by 2 meter. So the dimension and all the values here are not intended for very serious soil structure interaction analysis. It's just for ABAQUS tutorial. Okay, let's go start. Then first I will construct a soil domain, soil base. It's a 3D part. And the size is 30 by 30, no, 40 by 40. By 30. The depth is 30 meter. Okay. In the middle is the location of my structure and the location of my foundation. So I need to use some transition elements to connect the foundation and the soil brick element. I'm planning to use tetrahedron element. So tetrahedron elements are also using soil material, but it's using different element. So I need to create another part, and so I need to dig a hole here, and then after I creating another part, when I assemble all the parts, I can assemble it together. Okay, now I dig a hole here in the middle here, vertical on the right here. The dimension of the hole is 12 meter by 12 meter by 4 meter. The depth is 4 meter. First 0, 0, 12, 12. Okay. First, move this rectangle. Pick a start position here, and then I need to move this small rectangle to the middle of the surface. So the vector should be 0, 0. And the next point should be 40, 20 by 20, 14, 14, 28, 14 plus 14 plus 12 equals 40. Okay, yes. Okay, correct. The hole is down, so I need to indicate the depth. It's 4 meter. Yeah, now the hole is done. We need to create another part. soil with tetrahedron elements. The size is 0, 0, 12, 12. Okay. And the depth is 4 meters. I need to dig 4 holes, small holes for my foundation. So I cut this surface. This is vertical on the right. Okay. The size of the foundation is 2 meter by 2 meter by 2 meter. So here, first create a 2 meter by 2 meter rectangle, and then I move it to the bottom left. And then I move this small rectangle to, let me calculate, 40, 12. Just move to the right 2 meter and move to the top 2 meter. Yes. Here I use a linear pattern to create 4 footings. Spacing of the 4 footing is 6 meter by 6 meter. Okay, done. Depth is 2 meter. Make sure it's pointing downward. Okay. Okay, this part is done. I also need to create another part. It's a foundation part. It's very simple, just 2 meter by 2 meter by 2 meter. A cube. Okay. And for my structure on the top, I should use beam element, so I need to create beam element. All of my beam element is 6 meter long. I use wire shape because it's only a line. Start from 0, 0, 0, 6, 6 meters long. Yes, done. And another part for the column. Each story is 4 meters high, so the length of the column is 4 meters. Okay, all the necessary parts are created, so we move to the next module, property. We define concrete for the foundation and the structure. The density we usually use 2,500 kilograms per cubic meter. I'm using standard units, meters, second, and Newton for my model. Young's modulus, we usually use 3 times 10 to the power of 10. Poisson ratio is 0.3. We also need to use damping, but to correct input the alpha and the beta parameters for relay damping, we need to first run eigenanalysis. After we run the eigenanalysis, we will calculate alpha and beta, and then we input the alpha and beta here to run for the dynamic analysis. Usually in soil structure and interaction, people use plastic model, but here, for just the tutorial, I just use simple linear elastic model. Okay. For soil, I use 2,000 kilograms per cubic meter. Elastic, I'm using 2.6 times 10 to the power of 8 Pascal for Young's modulus, and 0.3 for Poisson ratio. Damping parameters, we will define it later. Okay. Then we create section for beam. We're using the same section for beams and columns. So we first need to define a profile. Beam, rectangular, 0.5, 0.5, okay. Material name is concrete. Done. Now the beam section is created. We create another foundation section. It's solid, 3D, so it's concrete. Okay. Also, we need to create a soil section. It's solid, soil. Okay. So now all the sections are created. We need to assign the sections to the parts. Do not create set. And I assign the column using beam section. I assign the beam using beam section. The foundation, use foundation section. The soil base, using soil section. Soil tetrahedron is also using soil section. Okay. Also here, for the beam, I also need to define the beam orientation. Okay. The column. Okay. After I define the properties, I go to assembly all the parts to get my model, my real soil structure interaction model, and I auto offset all the instances. Okay. First, I assemble all the big parts together. I put this. Here. Also put this. Here. I use linear pattern to create all the foundations. Okay. The underground structure is done, but I need to create the upper structure, superstructure. Here I only have one beam and one column, so I need to create a structure using just this now. Need to rotate this column. Let this column to be parallel to the z direction. Okay. Select the start point for the axis of rotation. I want to rotate around the x direction. 90 degree. Yes. Okay. I move this beam to be connected to the column. And I use linear pattern with this direction. I will select this direction. Reverse, okay. You also copy, use linear pattern to get another beam. Linear pattern. Get another beam. I rotate this beam around the z direction. Yes. Okay. Rotate. use linear pattern. This is the first story. The second and third story are the same, so we use linear pattern to get the second and the third story. The story height is 4 meters. Three stories. Yes. Now you can see the concrete frame is done. We can move it to the top of the soil. Now you can see the structure is situated on the foundation, and the foundation is situated on the soil, and the connected part we will use tetrahedron elements to model it. Okay. Let's define two analyses. One is frequency. We output 10 eigenvalues. It's enough. And seismic. Use dynamic analysis. Dynamic implicit. The duration of the ground motion we will use is 24.86 seconds. And we can use, because the time step for the ground motion is 0.01 second, so our initial increment is 0.01 second. The maximum, we can use 0.02 second, or we can just use fixed. We use 0.01 second as our time step. Here we just use automatic to maybe we will get the results faster. Okay. This part is interaction, and this part is the load. I'd like to apply the constraint and the boundary conditions on the nodes. So here we just skip these two modules and we directly go to mesh module. And after we mesh the model, we will go back to apply the constraint and the boundary conditions on the node, and also apply the ground motion on the bottom nodes. Here for this part, we will mesh all the whole model with parts. After every part is meshed, the mesh of the whole model is automatically generated. Okay, for this very small column, I want to use 4 elements. So the total length is 4 meters. So I wanna control the size of the element to be 0.8. Then the total number of elements is 5. Okay. Here I use mesh the part. Okay. Let's check the element type of this column. It's standard element library using beam. Linear formulation, shear flexible is using Timoshenko beam, not a Euler Bernoulli beam. Okay, good. Also the beam, the same thing. I want to use 5 elements for the beam, so the global size should be 1.2 because the total length of the beam is 6 meters. Okay, done. Mesh. Check the element type, beam, linear formulation, shear flexible. Okay. Let's go to the foundation. Here I want to use 4 elements in each direction, so the mesh size should be 0.5. Okay, down. Mesh, yeah, very good. Let's check the element type. Stress standard linear is using break element, reduce integration. We do not want to use reduce integration. It's an 8-node linear break element. Good. Then the soil base. You can see now the color is in red. It means it's not good for you to mesh right now. You need to partition this part into very small parts. These small parts should be very easy to mesh, and the color will also change to green. Okay, let's first partition this part, extend face using this face. Okay. Okay. Now you can see this part is green. It means this part is very easy to mesh. It's ready to mesh. Okay, you can see now this part is totally green. It means it's ready to mesh. I want to use 2 meter by 2 meter by 2 meter element size here, but strictly speaking, the mesh size should be decided by the wave propagation theory. You have the wavelength and you have your shear wave speed. You should use that formula to define your element size. Okay, here I will just use 2 meter by 2 meter by 2 meter. It's just a simple example, not some serious analysis. Okay. Okay, you can see now The mesh looks very nice. Check the element. Not reduced. It's an 8-noded linear break element. Okay. Then we need to mesh this transition zone. We need to use tetrahedron element. First, we need to cut this part into 4 small parts. Three points. First point, second point, third point. Okay. Select the cells to partition. Okay. 3 points. Okay. Okay. Here, to be able to perfectly connect these sides, and these sides to the large soil base, here, and here, we need to use 2-meter length mesh size. But to be able to connect these parts to the foundation, we need to use 0.5 meters mesh size. So we need to carefully handle this and need to apply some strict meshing size. First, I select all the model, the whole model. I use 0.5 for the whole model. Done. And then I change these edges to be 2-meter mesh size. Okay, let's do it. Let's go to the bottom first and then do it. Okay, here, 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 here. $2 Okay, looks good. Probably we can use edge angle. Okay, no. We need to use select individually. This one, this one, this one, this one, and this one. Okay, 2 meter. This one. When you press the shift button and then you click, you can click multiple objects. Meter. Okay. 2 meter. Okay, let's check my mesh size. The bottom is 2 meter by 2 meter by 2 meter. Okay, all the sides, all the four sides are 2 meter by 2 meter by 2 meter. Okay, it's done. Let's mesh it. Now we need to change it to tetrahedron elements, otherwise we cannot mesh it. We use linear formulation. Okay, now assign mesh element type tetrahedron. Okay, now you can see the color is not that red. It means now it's easier to mesh. Linear, we want to use linear formulation. Okay, let's try mesh. Okay, oh sorry, I need to delete this mesh. I need to change the mesh size at these 4 edges. These 4 edges, I want to use 1 meter mesh size. (1 meter). Okay. Mesh this part. Okay, now it looks very good. See the mesh. On the outer sides, it should be connected to the very large soil base. The size should be 2 meter by 2 meter. On the inner hole, it should be, because it should be connected to the foundation, so the mesh size should be 0.5 meters. Okay, our mesh is done. We will go to load. We'll go to assembly. Because all the parts are meshed, we construct the whole model. But we should. There's a lot of duplicate nodes at the same location, so we need to merge all the nodes. And here we can use merge and cut. After we merge all the instances, we will get a new part. It's okay, we will just simply use the new part. Merge the mesh, merge all the nodes. Okay, continue. Select the instance, this instance. Okay. The nodes will be merged. Okay to merge? Yes. Okay. Now you can see this is a merged model. We will use this model in the future. All the other instances will be suppressed. We can check here. Assembly, instances. All the previous instances are suppressed. And it creates another instance called part 1. It's just this one. Also the part, there's a new part. Part 1 is this part. We can go to the part module to see it. Part 1 is this. From part 1, we get this instance, part 1, part-1-1. Okay. Then we can apply our boundary conditions on the nodes. Fixed boundary condition for eigenanalysis. Okay. We select all the nodes at the bottom. Use angle technique. Okay. Select all the nodes. Use in-casture boundary condition. All the degree freedoms at the bottom are fixed. Then, so this is just for frequency analysis. We need to create another boundary condition for dynamic analysis. Fixed, except x direction, seismic, displacement. We select the bottom nodes again. Then we need to define a seismic wave, seismic equally spaced. The interval is 0.01 seconds. Boundary, the time history, displacement time history is here. We can simply copy all the values here, paste. Okay, this is the displacement motion. We use 1 here because we are planning to apply the displacement motion in the x direction. Okay. Then the last step, we apply the interactions, the constraint on the 4 sides. Here we want to use laminar box boundary condition. It means, for example, as we all know, in soil we have layers. One soil layer, so for a common soil profile, we have several layers. Each layer, the Young's modulus and the shear strength of the soil are different. So usually the soil will move a lot in the layers. So we'd like to constrain all the nodes at the same height, at the same elevation, with equal degree freedom. So other different elevations will have different displacement. Okay, I will simply show you how to do it. For equal degree of freedom constraint, we use multipoint constraint here. Firstly, we need to disable all the nodes except the nodes on the sides. I will use remove selected. I will select nodes. No. Select individually. We use this view. We change our view. Okay. Remove all the nodes except the nodes at the boundaries at the four sides. Okay. It looks like all the nodes are selected except the boundary nodes. Okay, we will simply remove. Now we can change the view, change it to the front view. Okay, and we apply the boundary multi-point constraint for each layer separately. We select the entities to remove, delete, select the multi-point constraint. Highlighting. Select the region for the slave nodes. We press the Shift button and select all the nodes on this layer. You can see all the nodes on the four sides are selected at this layer. So we can simply click down. We use tie. OK. Then we go back to the front view. Select one. Next, here's OK. Select all the nodes at this layer. OK. Use tie. OK. Create. Tie. First layer. Okay. Tie. Okay, the boundary conditions constraint are all created. We check everything, the part, properties, soil, sections are assigned, and oh, I forgot, because we create another new part, so all the sections here, we need the beam orientation, we need to reassign. Yes. First we did say remove all the useless elements. Assign the orientation for the columns. Okay. Change it to y direction. Okay. Then I can assign the orientations to all the beams. Okay. Good. Then check the assembly. It's done. Check the step module. frequency analysis, dynamic analysis, then the field output. I want to output the result at each increment, so I use it 1 strain stress. I do not need these forces. Okay. Interaction. All the multi-point constraints on the 4 sides. The load I have applied, the boundary condition, fixed boundary condition for eigenanalysis, and then the displacement motion for the dynamic analysis, then mesh, then job. Okay, first I will run the eigenanalysis, and then I get the natural frequency. I will calculate the Rayleigh damping coefficients. Submit. Monitor. Now the analysis is completed. We can go to, first we can view the eigenmodes of this structure. This is the first eigenmode. Done the move. Oh, should use a deformed structure. So this is the original model, and then the first eigenmode, second eigenmode, third eigenmode, fourth eigenmode, 6th, 7th, 8th, 9th, the 10th. Okay, let's check the eigenvalues. I will use the first eigenvalue and the first natural frequency and the third natural frequency to calculate the Rayleigh damping coefficients. The damping ratio I will use is 0.05 for the first natural frequency and the third natural frequency. Okay, wait for a minute. Okay, now I calculate all the two Rayleigh damping coefficients. This is for concrete. This is for soil. I input the two coefficients, and then save our model. Now the model is totally defined. It's SSI, soil structure interaction, I40 by 30 meter model. Elastic. Okay. Now we will define another job. We will activate the seismic analysis, and then we can run it. Okay. Submit. Monitor. You can see now step 1 is done, the eigen analysis. Now it's doing step 2. This is the increment, time increment. This is the total time the analysis has done. Okay, let's wait for a while, and then we will go to how to post-process the result. I will give another video on this. Okay, see you guys later. Bye.